All right, welcome back, everybody. So today we're gonna do this. We're gonna do two presentations first. First group and second group. I'm gonna then do my presentation, and then we're gonna do the second answer. Okay, to kind of like mix it up. All right. So, any questions before we get started? All right. So please, we're gonna talk about side channels, different ways of side channels. So this is actually a very interesting paper. So please, guys, stick to it.
All right. Hi, everyone. I'm Bill.
I'm Hana.
I'm Zahan.
And we're going to talk about some remote power side channel attacks for FPGAs. So a bit of background on what the problem is. So lots of cloud computing companies allow users to upload their own images onto FPGAs and system on chips that are part of the cloud computing environment. And a lot of times these FPGAs are shared amongst like multiple users. So it's not just one person, one FPGA. And so it's therefore possible to launch like side channel attacks against victim logic from other users that you're sharing the FPGA space with. And a lot of times these side channel attacks, which are based off of relative changes in power consumption of the FPGA, require specialized equipment such as oscilloscopes to conduct. But in this case, in this paper, they figured out how to do that in a remote manner that's entirely software based. A little bit of background, so CMOS power consumption. So in CMOS circuits, there's two major sources of power consumption, static and dynamic, with static power being related to transistor leakage when the transistor is in the off state, dynamic power being switching between low and high logic values. So charging the load capacitance that you see there and discharging it. And this is proportional to activity factor, clock frequency, VDD squared, and the load. And then a bit about ring oscillators, which is how they built the power monitors for their attack. So ring oscillators are basically an odd number of inverters plus an AND gate, which is used to drive an enable signal. The frequency of the oscillation is actually impacted by the supply voltage. And so when there's a drop in the voltage on the power distribution network, then the ring oscillators will start to oscillate at different frequencies, and they can measure that with a counter. So higher on-chip dynamic power consumption results in a lower frequency for the ring oscillator. And then this is a bit about the victim logic that the paper authors were attacking. So basically they had an FPGA-based implementation of the RSA trapdoor function that we learned about, specifically the inverse of it. And so they use this this square and multiply algorithm, which is that like big equation in the middle of the slide there. And this was basically implemented by two multipliers, which is a bunch of chained together adder circuits. And so they have a state machine that performs a computation for each bit of the key in a single clock cycle. And so if the current bit is 0, then only one multiplier is active at a time. If the current bit of the key is 1, then they're both actively switching. So they can measure that relative change in power.
Okay. So now I'm going to talk, one concrete example of FPGA to FPGA attack. As we learned in our lecture, in cryptography, side channel attack is going to be performed. It's going to exploit the weaknesses of the cryptographic system that are not related to the mathematical algorithms. Instead, it will utilize the information that leaks out from the operations, such as power consumption and also electromagnetic radiation. So in our case of RSA accelerator, the attacker is trying to perform the it's trying to capture the power consumption of our target FPGA remotely. So as Bill just mentioned, we can implement RSA decryption function on FPGA by a series of multiply and square function. So basically, we decompose the exponentiation into a series of 0 and 1. And for each bit of the private key, we have different power consumption. So this property makes our RSA core very vulnerable to simple power analysis attack. Basically, SPA attack can be done by placing a lot of power monitors near the RSA core on FPGA. So in this paper, the author performs attack in 3 different scenarios, where attack has full control over place and route, and another is there exists some physical isolation between logic regions with configuration logic blocks fence, and then another is the attacker has no control over place and route. So 10 different 1024-bit keys are generated to evaluate those 3 scenarios, and the number of bit errors and the number of power traces required to correctly get the private key are recorded. Okay, so here's one of the traces that we get through the simple power analysis. So from big wheel, we can see that there's a region where the frequency is lower compared to other parts of the curve. So in our power monitor, lower frequency corresponds to higher power consumption. So we can conclude that this part denotes one for modular exponentiation operation. And if we look into the zoomed in version of this curve, we can see that we can differentiate 0 and 1s from each other. And in this manner, the attacker can know the entire private key. Okay, so this is the results of the experiment. So through the analysis, we can see that even without some user-defined place and route constraints, the simple power analysis attack can still work quite well. So this makes this attack very universal and generalized. So the reasons are mainly because the individual variations for each power monitor is unimportant. We can always remove this kind of variation by taking the average. And another reason is that even if without any user-defined constraint, the FPGA synthesis tools will always place lookup tables of one individual ring oscillators near each other. So which makes the variations can be negligible. And also the impact of noise on SPA attack is considered in this paper. So we can find that if the randomly changing noise increases, we will need to increase the number of traces that required for a successful attack.
Okay, now I'm going to talk about the FPGA to CPU attack, and it is very common. It is very common nowadays that the modules on the same die sharing the same power supply, such as in this case, our just the test hardware is also this case. And we can also use the voltage drop caused by the switching activities, use the power monitor to make it visible. And firstly, the paper evaluated the effectiveness of the power monitor, and it firstly used the string compare to compare string with itself and as a function, and it also used the clock at time to compare. And we can see from the upper picture that during this period of the time, the power will drop a lot, and which represents the execution of the time of the function. And in order to test the effective accuracy of this power monitor, the paper also uses a long and short strings as an input to evaluate the accuracy. And we can see from the bottom picture that we can tell very clearly between the different different inputs. This is a short input and this is a long input, and we can tell very clearly between them. And we can also see from the picture that there are some absolute time shifts between the actual execution time and the power monitor output. We can see here is a shift, but it's fine. It doesn't matter because when we do the power side channel attack, we just cares about the difference time between the different execution and the function, but we don't care about the absolute time. And here is also an RSA example which used to attack the FPGA to CPU. And firstly, we have to know what is the timing channel mitigation, because when we want to get some confidential information when we want to get some confidential information, we can just give it an input and we can observe the time interval between the input and the output, and we can infer what is the confidential information is. But if we just force the time interval to be equal or to be a constant, we can just mitigate this attack. But if we use the FPGA to CPU attack, this kind of the protection can be broken. So here next is the below is the process, and we can see this RSA example. We should do the modular execution, and when the d equals to 1, its delay is different from the d is equal to 0. And if we want to do a timing channel mitigation, we just insert the delay function to make the delay of the bit to be the 1 and 0 to be equal. But if we use our FPGA attack, we can see from the picture that we can also clearly differentiate the 0 and 1 between them, because we can see from the picture that the first half has periods with the power consumption significantly lower than the second half. So that represents this higher output of the power monitor represents lower power consumption in the system. And we can also see from the picture that the periods with low power consumption are much shorter in the second half of the trace. That means no significant idle time, because there are some blank spaces between different peaks, but there are not some different some blank space. Although these periods are equal, we can also from the power we can also get the bits from the power consumption condition. And also here are some design part. There are also some other implementations, such as the delay line. The delay line's high level principle is the same as the ring oscillator, but the detailed process is a little bit different. And this delay line can also work very well. And here are some trade-off comparison. We can use we can see from the three aspects, such as the sampling frequency, the power resolution, and the robustness. And we can see that the delay line is more sensitive to some very detailed process, because we have to make sure that the delay of each element is equal, but it depends on the placement and the routing. And here are also some limitations about our FPGA attacks. The limitation is that we are unable to match the microvolt and the picoseconds level accuracy, and because we are always talking about the systems that integrate the CPU and the FPGA together, but it may fail in the systems utilizing the discrete CPUs and FPGAs. And it also has some countermeasures. The first is that we can insert some random noise and add some dummy operators, just as we discussed in the lecture. And we can also make the untrusted user difficult to construct the circuit, such as detecting the malicious circuits and disallow it. So here are some future work that is regard to the limitations and the countermeasures. Okay, that's all for our presentation.
Thank you. Any questions? Yeah.
So Not entirely sure if I understood what's happening, but it's for like enterprise or data center FPGAs, right? And isolating between different sections of the FPGA for different customers, right?
Yeah.
No, not necessarily. So it's more of an embedded FPGA. So the idea is like you have a data center, okay, with a bunch of different processors, and you will have some FPGAs also as kind of slots, okay? What these guys found was, first of all, between two different hardware implementation within one FPGA, there is leakage. But a more significant finding is the second part, which was there was leakage between CPU and the FPGA. As long as they are sharing the same power supply, what will happen is that if the CPU draws more current, it will impact the performance of the FPGA. How do they measure it? They use a ring oscillator, which essentially the switching frequency of the ring oscillator translates into how much power is being drawn. If more power is drawn, then the ring oscillator switch slowly. So they actually count that number and say, okay, oh, the CPU now is more active. My number is lower, so I'll find a relationship between these two to kind of understand it. They show it, for example, for RSA and other applications.
I understand, but renders my question invalid.
Other questions? And this is a very interesting paper because I mean, I showed you in the class that power side channel exists, right? And then we can use various different things. This paper takes it a step further and show that you can actually measure this remotely by using this kind of clever idea of using ring oscillators, right? So essentially your own power consumption is impacted by the other user's power consumption, and that's how you kind of understand what the other user is doing. So it's a true remote power side channel. Thanks, guys. That was amazing. Who's next? Shoot. All right, let's go with the second presentation. Yeah, just put it in the presentation mode so that you can see it.
Okay.
All right.
Okay. Hello, everyone. My name is Yili Tai, and this is my partner, Yuan Wang. And today we're going to talk about the paper, Platypus software-based power side channel attack on x86. So first, let's talk about the problem that this paper is addressing. So here's an intuitive fact: for different machine instruction, it generates different power. So can we exploit the information of the power consumptions and to gather secure information from the computer? So ideally, yes, but we'll face the several problems. First, is there any detailed analysis or profiling that results for different instructions? Second, is the power difference resulting from the different power instruction distinguishable? And the third, if so, then is there an existing system level method or tool that we can use to extract the information? Okay. So first, I'm going to talk about what information does the power consumptions tell us. First is the instructions. So, and it's very intuitive that different instructions generate different power. So from the figure below, we can see that the distributions of the different instructions and the energy it generates. Okay. And the second one is operands. Even for the same instructions, if it executes with different operands, it also generates the different energies. For example, we take the integer multiplication, for example. So the more, if the Hamming weight is larger, the Hamming weight means the number of 1 in the number. If the Hamming weight is larger, then it should generate more power. And the figure below shows the energy distribution from the different operands. So we can see the larger Hamming weight is, the more power it generates. The third one is the data value we load. So if the value, the Hamming weight of the value is larger, then we should also see the larger power is generated. And besides from the Hamming weights, the most significant bits, if it sets, that it also generates more power. And we can see that in the figure below. It shows that when the Hamming weight is larger and also the most significant bit is set, which is marked with the blue circle in the graph, then the power is larger. The last one is the cache status. We can also see if the data we loaded is cached or not. The reason is that because it takes more energy if we load it from DRAM. So we can see in the figure below, if it's a cache, it generates more less power, and if it's cache miss, it takes more power. Okay, so after we talk about the information that power consumption provides, now we are going to talk about how do we measure the power. This paper used Intel RAPL to measure the power. So Intel RAPL basically is a power meters, and it has the advantage that we don't need to access it physically for the measurements. And there's a disadvantage that it has a limited update rates. So the limited update rates will affect our power analysis and profiling. So for the Intel RAPL, the update interval is around 15 microsecond to 150 microseconds, and it's a very long period for the instructions. So if we measure it naively, then in this period, we'll measure different instructions and they generate different powers, so we'll get nothing from the measurements. So the solution for that is that we'll repeatedly execute one instruction for many times, and then we average the power consumption so that we can get the specific power consumption from the instructions. And I'm gonna let my partner Yuye finish the rest of the presentation.
So before we talk about how to do the attack, first introduce how does SCX works, especially for the SCX hardware. It ensures the information security in memory by only storing the encrypted data in memory. And before the execution, it will first verify the signature of the data and code to see whether it has been changed. And during the execution, every step it will just load the encrypted data and the code onto the processor, and use the case stored on the processor register to decode the data and code and to execute. Because no key and or the decrypted data or code are stored on the memory, so nobody can access the sensitive data from the memory. In this slide, I'll talk about how to build the attack block. The first thing we need to solve is the alignment. This is because we use the measurement in parallel with the SCX execution. So we need to know at which point of the measurement corresponds to the starting, which corresponds to the beginning code of the SCX. To do this, we need to create a power spec at the beginning of the SCX execution and use it as the mounting point of the measurement. The second problem is execution control. We want to have a boundary. The best one is instruction level execution control for the SCX execution. Because during that we can single step execute the SCX code one by one to get to the target instruction. And then we need to be able to repeatedly execute the instruction to memory. This is done by configuring the APIC interval panel. We set the time interval to be pretty short, shorter than two instructions latency or one instruction latency. If it's shorter than two instruction latency, we can configure it to execute one instruction for every interval. And if it's smaller than one instructions latency, we can just store its program counter or program pointer to this to be stay at the same position. And when doing this, we can eliminate the process of repeating this instructions execution and memory. Here is a case study of how to extract the RSA code from SGX. So for every bit of the sequence, which is real or here is a branch that based on the bit of the sequence, we either execute two instructions or one different instruction. So in SGX, we force a single step to the branch code, to the branch instruction, and then we use that the following instructions for some time and measure the power at the same time. Then we can use the power measurement to determine which part is executed, and then we can do the original sequence. This sets we also give some countermeasures to protect the system from the suction attacks. And the first one is to restrict the access from the real space. The second is to limit the measurement resolution. If it is closer than microjoule, then the attacker may not get the useful information to reduce such a suction attack. The third one is to add a new hardware register inside SGX, and this can help limit the real estate income. And by the time the authors publish their paper, Intel has also with their solution. We have made the microcode so that for the same instructions with different data or different occurrence. And if they are executed inside SGX, they are not distinguishable. Finally, it also lead to potential future works directions. The first is to transfer the circular attack to some other platforms that are. The second is to know how to distinguish the instructions with similar power. And in my point of view, these two questions actually lead to a more fundamental question. That's does the power difference still exist for the risk assay such as the risk fan? Because the risk assay compared to CISC assay they are smaller and more modular, so they may not have such distinctive power difference for different instructions, and such power side channel attack may not be true for such platforms. Thank you.
Questions?
What does the zero step mean?
What zero stepping mean?
Zero steps means every time when you jump back from the interrupt code, you have not finished the instructions, so it will resume to the previous processor state, and this is this has a same power like repeatedly executing the instruction, and then so if the interval is fully occupied by the same instruction, you can get a good environment of this power.
So they use this trick that, you have instructions run one by one, right? And then they use this on-chip sensor to read the power. Of course, if you read the power that way, the instruction goes really fast and your, power sensor may not be accurate because it update rate is like 1 microsecond or 1 millisecond, something like that. So in order to kind of fix that, what they did was this idea of zero stepping and one stepping, which essentially they forced the code to repeat itself over and over and over again. It can actually do it even zero stepping, which means that they repeat the same instruction over and over again. And then what they did is basically they measured the average power of that instruction instead of average power of the entire code. They force the instruction to just runs and runs and runs. They create an interrupt and then they kind of come back to the interrupt and then create another interrupt. So this way they managed to actually have a really good average of per instruction of that code. And then they showed all those, figures based on that.
Yeah, great job with the presentation. I know in the paper they mentioned that they submitted some mitigations to Intel in 2020 and then they patched it. Do you know if since then anyone has tried the same kind of attack or different attack?
No, I don't know.
There is another paper that came after a little bit that use another sensors. I also recently seen that temperature sensors have been used. But there is no public knowledge of whether or not somebody has used this, for example, for their attack or not. Unfortunately, since they don't have a footprint that who used this. But the good thing about this one is the patch is not that difficult because essentially all you need to do is making sure that by privilege level, at least you can read this, or you can make it like a little bit more noisier, things like that. All right, thank you guys. Okay. Okay, so today I'm going to, start a new topic and essentially talking about the isolation and attestation. Before that, I want to finish the discussion on, physical side channels. So the two papers you've seen today. So essentially, first of all, we show that power side channels and EM side channel exist, right? Because we do zeros and ones. There's different power for each one, P1 and P2. Somebody can measure this, right? And they can attack the system based on that, right? Measuring and attacking. So we discussed that. How do we measure this is really the question, right? So you can either have like a probe or a sensor nearby and measure this. This is kind of like a traditional way of attacking the systems. But the two papers that we discussed just now showing an alternative method of measuring this. The first one show basically that you can use an FPGA. And essentially, the idea of FPGA is that you have this SoC, this is your CPU, this is your FPGA. They're connected to the same kind of power source, okay? And what they did here is that they had like an array of ring oscillators. And this array of ring oscillator are basically just switching. The ring oscillator is just switch, okay? And what they found was essentially if the power of CPU, if the CPU draws more current, this frequency of these, goes down, okay? So the switching frequency of these goes down if there is more power throughout the CPU cycle. And this way, they kind of indirectly measure the power, right? Essentially, same idea as in like switching activity draws current, and I can measure that current. It's just a different way of measuring this. And the nice thing about this is that I can remotely, program this, okay? So this is, for example, an AWS instance. These days, you can actually have an FPGA in your cloud. So what you can do is that you can program this FPGA to have something like this and an array of inverters. And then you can measure that, and that way you can indirectly measure what's going on the CPU side. Okay, so that's kind of like the idea of that paper. The second paper is saying that, okay, I'm not going to use the FPGA, I'm going to use the CPU itself. But within CPU, there are a whole bunch of these performance counters, okay? There are a whole bunch of these sensors. There is like, performance counters to count how many cache misses you have, how many branch miss prediction you have, et cetera, et cetera. One of them is, well, for Intel in particular is this RAPL, which essentially measure the average power over some time. I think they have like, 1 microsecond average accuracy. This is kind of like for debugging purposes, you want these, because when you're developing your algorithm, for example, your benign and regular algorithm, you want to, for example, measure how much power your program is, consuming and so on. So for useful purposes, this is great. But what adversary can do is that the adversary can run a separate application here. So this would be the victim application, this would be an adversary's application. The adversary also has access to this sensors. So what they do is that occasionally they read this, and since this value is impacted by both this application and this application here, then adversary can essentially indirectly measure what's going on the victim application. Again, so again, same idea, switching activities, more switching activity, more power. I can measure power. So I can attack the system. Same idea, just the measurement is this way is slightly different. Okay, so that's kind of the idea. Of course, you need to be a little bit creative on how to measure. For example, here they propose the idea of single stepping and multi-stepping and so on and so forth. If you're interested, definitely go and take a look at that. But what I want you to learn is that there is this fundamental phenomena, and this fundamental phenomena can be used in adversaries' benefits in various different ways. Either physical measurements, remote measurements, FPGA measurements, sensor measurements, all of those things. Okay? Any questions? All right. So that's kind of it with physical side channels. There's also a counterpart for physical side channels, that is timing side channels and digital side channels. The difference is that it can be measured internally, not just because of the change in power, but more because of some different events that are happening. For example, let's say I can understand whether or not there is a cache miss or if hit in this program. Okay, so what can I do is that, again, if there are two applications, if this application do something like, if s equal to 1, do something else, do something else, do x, do y, okay? And now let's say, for example, if I do x, there will be a cache miss, okay? Because I, for example, read memory, okay? But if I do y, there will be a cache hit, okay? So what does this tell you? It tells you that, so this is basically the victim application, okay? So on the adversary side, all I need to do is that if I can measure the cache miss hit pattern, okay? If I somehow can measure this, then I can know whether X was executed or Y was executed. If I know whether X was executed or Y was executed, I know whether it's S is equal to 1 or 0, right? So essentially, if I see a miss, it means that S was equal to 1. If I see a hit, it means that S was equal to 0. And again, I'm not directly accessing anything. I'm just looking at the patterns that is available and shared. Why this happens? Because essentially, like cache, for example, is shared among different processes. So everybody can see the access patterns of everybody else. They cannot see the content, but they can see the access patterns. Okay. I'm not going to go through the details. We usually go like have a separate lecture for this, but we don't have time for this because I want to talk about other things. But if you're interested, there are a whole bunch of ways that different events, cache misses, misprediction, many other things can be used in order to detect that. So again, in principle, it's very similar to physical side channels that I showed you here, but instead of like zeros and ones and switching activities, zeros and ones creates different events. Event 1, event 2. Okay, event 1 could be a cache miss, event 2 could be a cache hit. As long as I can distinguish these two from each other, I can find what the underlying value is. Okay, any questions? So yeah, the timing channels is a story for another day. To get you a little bit familiar with it, your project 2 is about timing side channels, kind of like mimicking the behavior of what you would be able to measure. So yeah, there are 2 different parts: a memory side channel and timing side channel. So yeah, definitely start working on your computer assignment 2 to learn more about that. If you have questions, post it and start early, because I think the deadline is in 2 weeks. Okay, so I need some work. Okay, any questions? All right, so one quick announcement is that I'm traveling on Wednesday. I need to attend this conference, and exactly from 1:30 to 3:30, I need to give a talk. So I won't be able to live lecture this Wednesday class. So what I'm going to do is that I'm going to record the lecture, and I'm going to post it on the website. Just watch it, and if you have questions, just post it online. we can discuss things if you have any doubts on Wednesday, on Monday. Yeah. Okay, so no class, no in-person class on Wednesday. Okay. All right, so now let's talk about what we want to, what do we want to discuss today? So let's see what we have learned so far. So we have learned that there are attacks on the environment. These attacks are, can be, applied in the physical domain, could be applied in the analog domain, or even could be applied in the digital domain. And the attacker can also change things to create some intentional faults. And then the attacker can also directly interact with the system through the inputs or network and create memory faults and memory attacks, right? So extensively talked about this. Eventually, what the attacker wants to do is either confidentiality, integrity, or availability. And then usually this results in some form of malware being installed on your system and then attacking your system, right? So that's what we covered so far. And then on the defense side, solutions that we use is, of course, most of them cryptography can help. The other one is we use different prevention and detection methods at each different layer, right? We talked about like things like stack canaries, ASLRs, adding additional error correction and so on for faults. We talked about secure boot as a way to kind of establish some trust on the system before actually moving on and running things. So these are kind of like the solutions we talked about so far in the class. Okay. But let's now talk about what else we can do in order to improve. And these are mainly changes that we do at the software, the system, and the hardware level to improve the security. Okay. So 3 things that I want to talk about today and in the next lecture. The first one is, so we talked about kind of like the static behavior of the system through secure boots. But what if, for example, we want to occasionally check the system to make sure that there is no malware, right? So for example, I told you that, okay, there's a system and we're going to boot it, right? And during boot, we're going to do all those checks and say, okay, this system is secure, okay? Then we're going to hand it to the operating system, and then the operating system basically going to interact with this physical world, right? And then we said that there are various ways, including bugs, including human errors, and so on and so forth, that some malware managed to kind of install itself into the system, right? And at that point, the system is compromised, and we cannot do anything, okay? So the question is, can we do actually something such that, of course, okay, we do this and that's great and it works and so on, but can we occasionally check the system to see at least, can we understand this system has been compromised or not compromised? So we can do something about it, right? So can we at least detect the existence of malware in the system or not, right? So the question is that can we do some form of dynamic status checking? There are a whole bunch of remote devices, IoT devices scattered around. Let's say, for example, a medical device, a cyber physical system, so on and so forth. I may not be able to like eliminate the malware, but the least I want to know is that whether this device is compromised or not. If I know that, then I can do something about it, right? I can update it, I can reset it. At least I cannot use it, stop using it, so on and so forth. Okay, so that's one. The second thing is that we talked about all these, memory corruptions, ROPs, buffer overflows, and so on and so forth. And we talked about this, that maybe we can do things in order to detect the violations, right? So if there is like a control flow and there is like an incorrect jump, or there is an invalid behavior, maybe we can do that. So maybe we can add some hardware support and some techniques in order to detect that as well. Okay, so that helps us to completely avoid memory corruption. And finally, can we actually isolate, processes and systems from each other? Why? Because of 2 reasons. One is if the system is compromised, right? If the system is compromised, if I have like some part that is isolated from the rest of the system, maybe I can still protect this from a compromised system. Okay, we usually call this enclaves. Okay, so essentially these are these are part of the system that the hardware is like literally physically separate from the rest of the system. So even though that this part is kind of compromised, I'm still can't trust kind of like this part of the system. Okay. So how can I implement that? How can I use that? And then another thing that you want isolation for is the opposite of what I said, which is essentially if you have a system like this, that you have, for example, a program that is kind of compromised, how can I protect the rest of the system essentially from this compromise, right? So kind of like, confining the virus, right? So if something is infected, at least I might want to confine it and not let it to spread throughout the system, okay? So this is kind of like the opposite of this. This one is the system is compromised. I want to protect my single one, application. On this side, the application is compromised. I want to spread, stop the spread from the rest of my system. Okay. So all these three things require some form of hardware support, system support, and software support. And they all goes into this, realm of attestation, isolation, and trusted execution environment that I'm going to talk about in this lecture and the next lecture. Okay. So let's just start with the first problem. Let's see how much we can basically cover today, and then I'm going to cover the rest, and then I'm going to talk about the other two problems in the next lecture. Okay. So status checking. Why do we need it, and why it has to be remote? So as I said, the biggest issue that we have, remember, we are mainly talking about edge devices and IoT devices in this course. We're not talking about like stationary devices. So the kind of like the paradigm that I pictured for you so far is that you have a bunch of these different devices, kind of mostly mobile, scattered around, medical devices in the hospital, in-body devices that you might use for medical reasons, cyber physical systems that you use in industries and offices, a bunch of different smart home applications that you use at home. So all of these devices are kind of remotely connected to some internet and some centralized server, but they are interacting with the open world, and they might be compromised. So you want to know, for example, that okay, these 10 devices that I have at home, are they still the same as when I use them during the secure boot or not? Have they been changed or modified in any way or not? Because if I can get some guarantees that the memory, the status of this device hasn't changed since then I'm kind of secure against malware, at least at the time of the check, right? And then why it has to be remote? Because as I said, the paradigm that we're talking about is about edge devices and IoT devices. So these are devices connected through the internet. So this status checking needs to be remote. I cannot really physically go and check the device. I need to be able to do it hundreds and thousands of miles away from the device so that I can basically say, okay, these 10 devices that is under my control, they're all good or not good, and so on and so forth. Okay, so that's kind of like the motivation. Examples, there are many. The most famous one is probably Stuxnet that you have heard about. I think we briefly talked about it last time about when there was PLC. So PLCs is kind of like this, one of the very common examples of the cyber physical systems that we're targeting in this class. They used to kind of like, control different physical sensors and actuators, open a valve, close a valve, read the sensor, change that temperature, these kind of things, move that, motor, all those kind of things. And they can be used in many, many systems. Most of, industries use them for various reasons, including critical infrastructure such as, power generators, nuclear energy generators, and all those things, okay? So it would be interesting for an attacker to change this, because if they manage to change the software or the firmware of these PLCs, they can actually run an attack. For example, this is a real attack. That what they did was these PLCs were controlling the centrifuges, this motors that's kind of like, rotating with some speed. And they managed to very complicated, like multi-step attack that starts with a worm and then install another virus and so on and so forth. But eventually what they did was, so this was the PLC, really the CPU. And then there was this firmware within the CPU, and all they did was they replaced this firmware with another firmware, essentially. And then this is kind of like the malware that they managed to install. And what this malicious, malware did was just, rotating this centrifuge faster or slower than what it's supposed to. It's really what it does. And as a result, this is very, very sensitive, very critical process. So slight change in speed can have a, big, avalanche of catastrophic events. And then as a result, it's kind of like explosion and all those things. But in the pure, CS perspective, all they did was they essentially change this firmware to another firmware. So firmware 1 was changed to firmware 2, right? So what we need to do is that if we are able to detect these kind of changes, then we can, detect that, this PLC, for example, is compromised. I can stop using this, or I can go and actually change it, right? So I need to know the status of my CPU at each time. I need to know what is installed in this system. If I know that, then I can do something about it. Okay? So that's kind of like the idea of what we call remote attestation, that we want to attest the status of a remote device. The goal is we want to know whether the device is compromised or not, or in other words, we want to know whether there's any malware installed in this system. Okay, and the frequency of this remote attestation depends on the protocol that we are using. We can do it every month, every year, every hour, every second. We can do it at each particular time. For example, if there's a code update, you can do it in various ways. Okay, I'm not going to talk about that protocol. There are known works for that. But the idea is that if we want to do it one time, how should we do it? What are the requirements? What are the attack scenarios, what we need to add, and so on and so on. That's kind of like the idea that we're going at. Okay, let's have a quick break. I'm going to come back, talk about this, and then we're going to continue the presentations. Okay. So I kind of like, tell you why we need remote attestation. So let's see what it is, what's the requirements, what's the plan, and so on. Okay. So remote attestation, think about it as a two-player game. There's a prover and there's a verifier. Okay. The prover is the device in question, is a remote device. Think about it as the PLC or the medical device that you want to ask. The verifier is a device that verifies, obviously. It's a device that we trust, okay? So we trust this device, we don't know whether we can trust this device or not, okay? Then the attestation process is essentially a measurement process. The prover needs to measure something, provides the results, and verifier has to check that measurement and see whether that measurement is correct or not, okay? And that's kind of like the idea of attestation. How do we do it? Essentially, the goal, if you think about like what we want to achieve here, the goal is I want to know whether the content of the memory of the remote device has been modified or not. Right? That's really the goal of this process. So I need to show as the prover that here's the content of my memory, and see it's not been modified. Okay. So how do we do it? A very simple approach is that I just send out all the content of my memory, and you can basically, like as a verifier, you can actually go through them and see whether they have been modified or not. But this is not the very best, way of doing that. It's not very economical because we're talking about, megabytes and megabytes of data. If you want to send a megabyte of data over the air, especially for like an IoT device, that doesn't make any sense. So instead, we use hash functions, another use case of hash functions. So what we do is that we compute a hash over the entire memory. We just compute one hash. And essentially, our hash would be kind of like a chain hash. So let's say this is my memory. Let's say these are the lines. Let's say 4 lines. But of course, there's like many lines. And I have a hash function. So what I do is that I read the content of this. Let's say this is, for example, an 8-byte data. So I compute the hash function of this. This would be hash 1. Then what I would do is that essentially this would be the input of this, and this would be the hash 2. And then the input of this to this would be hash 3. And then I essentially repeat the hash function process each time with a new input and the previous input as the two inputs to the hash function. If you remember, the hash function was literally this two input system that takes some form of a seed and some form of input and then results in output, right? So this is kind of like the idea. I start with, like maybe I start with a random seed here. I take the one of the first line, compute the hash, use this as a new seed, take the next line and compute this. And then at the end, I will have just one hash value, right? That one last hash value is the value that I'm going to send to the verifier. The verifier going to also compute the hash and then check this hash is the correct hash or not, right? Because the verifier knows the correct content of the memory, right? The verifier knows what is the baseline, what is the unmodified version of this memory. So they know what the hash should be, right? So they compute this hash with that expected hash. If these two value matches, then we're good to go, right? So that's kind of the idea of a simple idea of attestation. But of course, this is assuming that nothing bad will happen. The adversary does not try to attack this, which is not true. So we need to actually make this process a little bit more complicated. Okay. So the threat model that we have in the system is that we are assuming that the system is completely compromised. Okay. And our attestation should work still under this completely compromised system, which means that if the adversary changed something in the program memory, that should result in a different hash than the expected hash. If that works, then our attestation is secure. Okay. And remember, the adversary has complete control, so they can basically cheat, they can lie, they can forge, they can do all those things, and still under those assumptions, I want this remote attestation to work. Okay. So that's kind of like what we want to achieve in the system. Okay. So what are the attack scenarios? Based on what I showed you here, tell me in scenarios as an attacker, how the attacker can cheat this process. There's two simple ones. Let's see.
Whenever the verifying device asks for the hash, it lies about what the hash is and uses the old one.
Use what?
Uses the old hash.
Yes. So I use the old hash, right? So if I need to compute the hash, I change the memory, but I keep the copy of the memory somewhere. For example, I just lie hash, right? So that's one. And the second one, any suggestion? So I forge the computation. So I don't repeat, but I forge. So for example, for the repeating, the simple solution is that, I use a nonce, okay? If I use a nonce, if I use a random number each time I'm seeding the hash, then as long as I'm changing that nonce, the final hash value would be different, okay? So going back here, so I told you that there is like an initialization vector or a nonce here, right? And this nonce results in a different hash, okay? So I'll add to kind of avoid this replay attack. What I'm going to do is that the first time I send one nonce, then the second time I provide another nonce and another nonce. And this just guarantees that the hash will be different, the hash 1, hash 2, hash 3, and 2. So the attacker cannot do replay attacks if we change the nonce, if we initialize the hash function each time. But in addition to that, the attacker can basically what we call forging it, which what they do is they can have a copy of the memory somewhere else. And when I'm asking to give me the hash, they don't give me the hash of this memory. They give me the hash of this memory, the original memory that is stored somewhere else. Either in another device, another remote device, or somewhere else in the program memory, and so on and so forth, right? So the response that I'm getting is the correct response with the correct nonce, but the computation has been cheated. The integrity of the computation itself is not valid, okay? So to kind of like summarize, there are two classes of attacks that we are worried about. The forging type of attacks, where the adversary kind of like use various different techniques that I'm going to talk about in order to kind of change the way that the hash is computed. So they're not really doing what they're supposed to do. They cheat the process. Or they just don't compute it at all. They just find an older value and just send that to me. Okay, so either of these. For the first one, we're gonna do a nonce. Okay, so what we're gonna do is that for the to kind of avoid replay attacks, we're gonna make sure that no two attestation results in the same, output. If we make sure about that, then older value no longer is valid. Okay. So in other sense, we are creating what we call a challenge response paradigm. Okay. So how does it work? Remember, I told you there is a verifier and there is a prover. So the verifier say, okay, give me the hash, and the prover provide the hash. So instead of just saying, give me the hash, I'm going to send a challenge. And what the challenge is, think about the challenge as simple as just a nonce value. Okay. So I'm going to tell the prover that compute the hash of your memory based on this initial value that I'm telling you. Okay. So it's not just compute the hash. I'm telling them what is the initial value of the hash is, and then saying that, okay, compute the rest for me. All right. This way, as long as I'm changing this nonce each time, it is guaranteed that the hash would be different. Hash 1, hash 2, hash 3, and so on and so forth. Same idea that we use for encryption. As long as I'm changing the nonce, it is guaranteed that the encrypted value is different. And in this case, it's guaranteed that the hash value would be different. Okay. So we call this a challenge response. Basically, this is the challenge that we are sending. In this case, it's just a different nonce value. And the response is the corresponding hash based on the content of memory of this prover and this nonce. So together, they results in a different hash. Okay, but that's kind of the idea that we are going after. All right. Any questions so far? Good. Okay. So how about forging? So the forging is basically is saying that, I'm just getting the hash value itself is not going to help. Why? Because we're assuming that the university can control everything about that remote device. Okay, we have no idea what sort of malware has been installed there. The malware could be so powerful that essentially the entire attestation protocol no longer actually works for it. Okay, so in order to kind of like get some confidence about the results that we are getting, we need to kind of basically check two things. Okay, so we need to check the response and compare it with the expected response. This is the hash value based on the nonce. But in addition to that, we need some evidence that this hash has been correctly computed. Okay, and we need to achieve that remotely. And that's kind of like the complicated part of this remote attestation. But we need to kind of say that, okay, they have really computed this hash correctly based on the protocol that we tell them to do. And this is really the results of that. And if the results of that is indeed correct, then we can trust. So the trust is a two-step phase. It's not just the result. It's also the way that they computed the results is important. Okay. So there are three different ways of achieving this. There is using pure hardware, okay, which is essentially kind of similar to the way that we did it with TPM. There's pure software methods that we call software attestation methods that I'm going to describe. And there's kind of like, a middle between the two, which we call the hybrid method that use a little bit of hardware and use a little bit of software. Since we don't have much time, I'm just going to explain the hardware method for you. And then on the next lecture, I'm going to talk about the software method and the hybrid method. All right. So what is hardware remote attestation? The hardware remote attestation basically says that let's have a dedicated hardware in the remote device that does the attestation for us. How do we do that? Remember, we talked about trusted platform modules, TPMs. And we already have that, and let's say that works perfectly well. It cannot be, compromised and so on. So what we can do is saying that, okay, TPM, you are responsible to do the sequence, secure booting for us. How about you actually do this for us as well? Do the remote attestation for us as well. Okay. So for that, what do we need? We need TPM to be able to kind of expand a little bit such that it can actually run arbitrary code, because they need to run some hash functions. They need to kind of contact with a remote device, right? So they need to have access to the network and so on and so forth, right? So since this is a remote attestation, you cannot just compute. You have to compute and send, right? And then this send part also has to be part of your trust zone. So you need to kind of like expand the notion of TPM, and this is what we call a trusted execution environment, or T. So essentially, T is this units within hardware that expand the idea of TPM so that you can actually run dynamic code, run arbitrary code on TPM. There are various design considerations and so on and so forth. And we're going to get back to this T's later on, because T's also give us the isolation that we want to. So T's are really useful in many, many cases. Okay. But the problem with the T's is that it's not straightforward. It requires lots of power and area. It requires lots of extra hardware. And then we are talking about like low-end IoTs and cyber physical systems. Usually using a trusted execution environment is not the best choice because it requires lots of extra things, okay? Because of that, we usually go for software attestation and hardware attestation, hybrid attestation. That kind of like sits somewhere between just a full-on dedicated hardware that we use in high-end systems. In high-end systems, we have things like SGX that we actually mentioned this during one of the presentations. We have things like Trust Zone. AMD has this thing called SEV. So there are a whole bunch of things that at the server level we have that give us this functionality. But when we go to IoT devices and low-end devices, we don't have those. Okay. So I'm going to pause here so that we can continue the presentations. But what I'm going to do is that I'm going to finish this lecture offline. And then I'm going to also discuss the other 2 points that I wanted to discuss: isolation and control flow attestation. And then going to post that video on the website so you can watch it. If you have any questions, definitely post it on CampusWire. So just a reminder that there won't be class on Wednesday. Okay. So just before we go, let's do the participation as well. Today we're going to do lectures. Go lectures.
Hey, I did not do it.
You want to lose points?
I'm wearing my click shirt today.
That's why. That's the motivation.
Just a slight.
You can do the Go Warriors.
And then I'm not gonna. Is there a space?
Yes. All right. So who's the third group? Can you please? All right. So let's continue with the presentations. The last two. Yeah, you have to disconnect the audio, I think. Yeah. Go to Zoom and disconnect your audio so that you don't see that. And then disconnect the audio. Oh, it's I cannot read it. All right, please go ahead.
All right. Hey, everybody. So I'm Tim. And we're going to present Cache Bleed, a timing attack on Open SSL constant time RSA. So,
Yeah.
Some feedback.
Yeah, I think it's still your, you or one of you two.
No,
I think it's fine.
You have to just disconnect the audio, otherwise. Right. Oh.
Okay, cool. Okay, so just to summarize the attack, so Cache Bleed is a timing-based side channel attack on Open SSL. Basically, it exploits certain cache vulnerabilities in order to recover secret information and ultimately recover the private key. The main thrust of the attack is that it's creating timing variations in cache memory access requests and using that to leak secret information. So the specific target of the attack here is the modular exponentiation operation of the decryption process in Open SSL RSA. On the hardware side, it is targeting specific Intel architectures like Sandy Bridge and Skylake. Okay. So cache attacks in general, and this one specifically, assume that the attacker is located on the same machine, is basically sharing a processor core and has access to the same processor cache. The attacker can observe access patterns to the cache in order to recover secret information, in this case, recover a secret exponent, and use that to recover the private key. There is a countermeasure that this specific attack cache bleed is meant to counteract called scatter gather, which we'll cover a little bit more in detail later. And there are basically two flavors of this attack, exploiting two different vulnerabilities. One is cache bank conflict, where essentially there is a limit to the number of concurrent access requests that a given subdivision of the cache can service at the same time. And so if you exceed that limit, some of the requests are delayed, which creates a timing variation. And then the second flavor is creating false dependencies. So read and write operations can't be executed simultaneously if there's a certain amount of overlap in the addresses in case that there's a dependency. So you can create false dependencies and create a timing variation that way. So specifically, this attack is targeting the modular exponentiation operation. So for this operation, there are pre-computed multipliers that are stored in the processor cache and then are accessed repeatedly. The goal of the attacker is basically to determine that access pattern, determine which multipliers are being accessed and when in order to recover the private key.
Okay, now I will talk about how does cache leak our information. So in a conventional cache model like this, the multipliers are stored in across different, stored in consecutive lines. So as shown in the picture in different colors. So if the attacker preload data into the cache, and then when the victim program executes, then some of the data will be replaced. And afterwards, if the attacker accesses the data again, you can figure out what are the ones that takes longer to access, and those will be the ones that will be replaced. So this is how we identify the location of the data. One way to prevent this persistent attacks is to use the scatter-gather implementation. So if we break the multipliers into at bit level and scatter them across different lines, and then essentially one line could only contain one bit of useful information, and then it would be essentially just useless to know which lines are accessed. It's a commonly implemented approach to prevent cache-based timing attacks, but there's also limitations. So to improve the cache bandwidth, Intel proposed the idea of cache bank. That is the new cache design that consists of different cache banks. So each bank serves as part of the cache line, and then they can work concurrently and independently. But one cache bank can only serve one request at a time. So that's when the cache bank conflict happens, and the timing channel may leak lower address bit information. Now I'll talk about the Open SSL scatter-gather implementation. So instead of scattering the multiplier into different lines, we first divide them into 64-bit fragments, and then across then scatter it across to different groups of 4 consecutive lines shown in the picture. There are 4 bins in each line, so we need 3 bits to do bin selection, and there are 4 lines, so we need 2 for line selection. And then, for example, this 11001, the 11 is line 3, so and 001 is bin 2, bin 1. So it's essentially the purple one, the multiplier 25 from bit 0 to 7.
So now I will talk about how the cache bleed attack works. So to understand that, we have to know that the attacker and the victim program, they will run in a same core and they will share the cache. So basically the attack is do a very simple thing, like he is trying to keep loading all the data in every cache block. So he keep loading it. And once the victim trying to accessing data, there will be a cache bank conflict. And the attacker will notice that, oh, maybe this line is, the data comes slower, so this line must be used by the victim. So he can identify the location of the data. And in this paper, the researcher have defined like 5 scenarios, and the first 3 is like they found like if the victim has a memory operation, they will greatly increase the time cycles that the attacker needs to access to data, load the data. And they also found like the computer operation will also affect the time, but only slightly increase the time. But they do a very important scenario. They found a very important difference between the scenario 4 and 5. Basically, these 2 scenarios is like they do the mixed load, but one with the cache bank conflict, one without. So they found there is a small overlap between them. So which means you cannot tell there is a cache bank conflict or not by using just one single measurement, because there is a small overlap. You cannot say there is a conflict. So you need to do the test many times and do the average and see the value. So how can we use the time variation to find the bin? So here is a small section of the trace of all bins. So we can see in the second and fourth multiplications, the measurement in bin 3 takes longer than other bins. So which means the victim programming is trying to use the data in bin 3. So that will take longer for the attacker. That will take longer to read the data in bin 3. So that's indicating the last 3 significant digits in this program should be 0, 1, 1, which means 3. So that's how we identify the bin. And also, it's relatively hard for the computer program to tell which bin the.
You want to put it maybe on the.
Yeah. So which bin takes longer to complete certain modifications, because due to the other factors like OS iteration and some ALU computations, they will introduce very high frequency noise. So a single measurement is not enough. So they need to do a lot of tests, and because you need to do a lot of tests and do the average, you want the signal be alignment. So you also need a program to identify what is the start point of each modifications, what is end point of each modifications. And you also need to put the raw signals through a low pass filter to clean all the high frequency noise. So after all those steps, we can see the signal is very smooth and beautiful. Maybe, I don't know if you can see the colors, but it's very straightforward. Like this is a 7, the pin 7 is like black one, and 751. So that's the results, very straightforward. So with this partially information, because like in this task they have 5 digits,
and we can only read about 3 digits from the attacker. So how can we use the partially information to recover the private key? So basically, the researcher just brute force every possible solutions for the RSA private key and use the last 3 digits as a verifier. So we will keep trying to verify the result. And with the verified informations, they can use an algorithm called branch and cron algorithm to greatly speed up the whole session. And the full search only took about 3.5 minutes to find the private key, and they can just use like 16,000 decryption to find the key. And the conclusion of this paper is this paper provides a feasible way to implement the side channel attack and also demonstrates this method on the actual hardware. Also found a problem in the OpenSSL RSA implementations. And they also points out 2 countermeasures. The first is disable the hyper threading function so that the attacker and victim will not share the cache. And also you can increase the bandwidth of the cache banks. So that it's for the attacker, it's hard to read the exactly data and to record the time of each data load time. So yeah, that's basically the countermeasures they proposed. And that's the end of our presentation.
While we're answering questions, can the final group, the 4th group, come and set up so that if we're kind of on front. Any questions? This is kind of relevant to what you're going to do for your, computer assignments. Not exactly this, but generally the idea of timing channels is what we have. Yeah, questions.
Yeah, it's a great job with the presentation.
Can you stop sharing so then?
Both of the mitigations that you just mentioned, I think make sense to bring in new processors, right? Like obviously, and I imagine that Intel doesn't want to disable hyperthreading. That's how they. Do you know if there's any retrofit thing that you can do to prevent cache bleed other than just disabling the feature entirely?
Not that I'm aware of. No, yeah, not for older architectures.
Yeah, and unless you do the way, you make it oblivious to kind of cache lines or kind of randomize it, things like that if you can do. But other than that, yeah.
So you can't like change the cache bandwidth size from software, right?
Well, they have like you can patch it if you want to, but it's keep in mind that you want it for performance reasons.
Yeah.
Like all these things that they do is doing it for performance reasons. So you can kind of like make it slower or eliminate it, but that will result in significant hit in your performance. All right, thank you guys. So you have 10 minutes.
Okay, so I'm Vincent and this is Jason Graham, and we're presenting wireless charging our side channel attacks today. So let's start with the problem. Well, the problem is as follows: when you charge your phones, right? So what if we use our phones while we're charging it? Would the resulting power statistics leak enough information for an adversary to extract specific secrets? Well, in traditional wired charging, the answer is mostly yes, and it's demonstrated at this point. But what about wireless charging? Since it's inherently a noisier interface, it makes some sense that people have considered this to be secure against practical side channel attacks in the past. But as shown by the authors of this paper, this is in fact not the case. So, oh, wait a minute, something's wrong here. Here we go. So the problem stems from where when a battery starts charging, it provides full current to the battery. It makes a lot of sense because you want to charge the battery fast. But as a battery drains power, the voltage drops and vice versa. So when you hit the points when the battery starts to have fixed voltage in this region of a charge. Since the wireless transmitters, they don't hold a lot of charge in them, the current provided by the power supply would actually reflect the amount of power used by the battery provided device. So we can in fact extract usage information by monitoring the current information that we have in our wireless power transmitters. And we would be able to infer these usage statistics for the victim. So next up, I'm going to explain the threat model and the problem that this powered side channel could allow. And oh, there's also going to be cats, so don't worry about it. So let's say we have a smartphone, our victim, and it's within close proximity to a wireless charging device, specifically 4 centimeters. This is more so a limitation on the QI wireless charging standard than a limitation for this particular attack. So we have this transmitter connected to a malicious public charging station, and a side channel leakage of current information to a malicious monitor within the wireless charger. We can actually train a classifier that would infer like specific information from the statistics, like say the whatever specific web page the user is currently browsing. Or if this graph is way too confusing to read, this should be significantly more readable. And something to note here is that this can be done without fully like a bulky equipment or oscilloscopes, and can be. This would mean that identifying a malicious charger for a everyday user would be extremely difficult, since it's possible to tightly integrate this kind of a system into existing microcontrollers within wireless charging stations, and which of course makes it small. It should be also noted that there is no need for the victim device to be in any way plugged into the charging station itself. And there is no need for the victim to carry malicious software. It does not depend on any software vulnerabilities and does not require any physical tampering to the target device or its battery, since it entirely depends on the monitoring of current and, as we explained earlier, power draw.
Right, so as mentioned, the author's primary contribution was to show that power analysis attacks can be done on both wireless or the wireless charging systems, just like they can be done on the wired charging systems. In order to show this, they needed to set up a test bed. So they took 2 different wireless charging pads, an Anchor 10-watt charging pad and a Adafruit QI compatible charging pad, like shown here, is basically just a little cardboard circle with a wire going through it. But they then took 2 phones, a Pixel 4 and an iPhone 11, and put them in a default state. This was pretty much just with Bluetooth disabled, the cell service disabled, but the Wi-Fi enabled. And then they wrote a script to visit a website 50 times repeatedly, and they would give it 10 seconds of loading and 4 seconds of waiting. And they used for Apple a web inspector, which is very similar to Chrome's DevTools, which they use for the Pixel 4, to link in and automate this process of visiting a website. And with the setup, they also had a current sensor put in series with the wireless charging pad, right? So they could record the current trace that was coming through here. So over here on the left, you can see the resulting current traces. And you'll notice that on the same website, you can see the same pattern, but between different websites that are visited, they are significantly different, which gives them reason to proceed with this sort of data. And they decided next to launch a website fingerprinting attack. This is basically where you use some loosely related data to the website being browsed on somebody's phone, and use that data to try to figure out what website's actually being visited. And you're basically revealing a user's private browsing data, right? So in order to do this, they classified, or they used a 1D convolutional neural network, and they classified the top 20 websites, but then they later did the top 50 websites from Alexa's top sites in the United States. And they took their current traces and split them up into 1 second segments. And then they split their training data into 64, 16, 20 split, and trained their 1D convolutional neural network with pretty good successes.
All right, so now that we have a good idea of how the system works, let's look at the results. But before we do that, let's define some key terms that they use throughout their paper. So first of all, is this concept of noiseless. As we know, our cell phones emit a lot of wireless signals, such as Wi-Fi, Bluetooth, or LTE, and these can interfere with the current draw as well as interfere with the current collecting system. As a result, when the authors talk about noiseless, in this case, Bluetooth will be disabled to try to minimize interference. There's also this concept of rank 1 accuracy, where we have our classifier, we just take the highest confidence output and we see whether it's correct or not. This contrasts with rank 2 accuracy, where we take the 2 highest confidences, and if one of them is correct, then we count that as a correct prediction. So let's look at the results that we obtained on both the iPhone as well as the Pixel. In terms of the iPhone 11, we can see a comparison between the noiseless wireless traces as well as the noisy wireless traces. And we can see that the noiseless ones perform slightly better, which makes sense because the classifier just has less junk to sort through. On the top, you can also see the trace duration, which is how long the signal that was fed into the classifier was. As we start from 10 seconds and we move our way down to 2.5 seconds, you can see that the classification accuracy begins to degrade as the signal gets shorter and shorter. However, even in the worst case, for the noiseless wireless trace at 2.5 seconds, you can still see that we can achieve an accuracy of 80.5%, which is pretty good. It can still fingerprint a lot of information and reveal a lot of the user-sensitive information. You can also see this for the Pixel 4, where the lowest at the wireless rank 1 at 2.5 seconds is over 85% as well. The authors also evaluated something known as cross-domain training, where they train on wireless traces, but maybe try to evaluate on wired traces to see if there's any difference. So here's a confusion matrix showcasing the result. The diagonal of the confusion matrix essentially shows a tendency of a website to be classified by itself. For example, in this case, there's an 86% chance for Amazon to be correctly classified. On the other hand, a website like Bing, for example, in 72% of the times, it's actually misclassified as Amazon.com. So we can see that this cross-domain training works for some websites, but not for all of them. The authors also evaluated the impact of battery level. This current trace shows the battery level at approximately 99%, and you can see a large amount of current amplitude. For example, starting from here, you have almost 200 milliamps of current variation. Unfortunately, once the battery level starts dipping below 80%, your current traces become a lot smaller, and it becomes very difficult for any classifier to extract useful information from these current traces. Some future work that the authors in the paper talked about and that we thought about as well. So the first one that the authors talked about in the paper was potentially using this system to break RSA, which is very common for a lot of these power draw side channel attacks. So you can see in this figure that from this wireless charging attack, the authors are actually capable of extracting the difference between the idle operation, a square operation, as well as the multiply. However, due to some timing issues with the sampling rate of the microcontroller, they were unable to implement a full attack breaking RSA. Furthermore, we also thought about a potential future work involving devices with dynamic refresh rates. For example, on a lot of modern devices, if you touch the screen, the refresh rate will jump to 120 Hz, requesting additional frames from this buffer. We were wondering if this would somehow be reflected in the current trace as well, where we can actually look at the current traces and see if we can infer user input to extract passwords or something that they typed in. In terms of some discussion points, first, we want to talk about feasibility. How feasible is this attack? For example, because it requires your phone to be above 80%, if your phone's at 90% and you see a wireless charger, are you actually going to be inclined to use that for charging? Furthermore, there's also the idea that you should try not to charge your phone above 80% due to battery degradation, which would probably limit the effectiveness of this attack. Furthermore, we also have the issue of practicality. If a user does decide to charge their device, is it easy for them to use while it's charging? Because if we place it on a wireless charging pad, it's a bit awkward to try to type in it. And users will want to pick it up and type with it normally, which may limit the effectiveness of this attack and make it difficult to actually execute. And finally is the issue of generalizability.
They tested it on close to around 20 websites. However, if you try to expand this to 100 websites, it's almost guaranteed that the classification accuracy will drop because now you have a lot more chances for websites to have current that looks a lot more like one another. So these are just some questions that we want you guys to think about for the discussion point. And thank you guys for listening, and we'll be open for questions and answers.
Questions?
Yeah, great job. I thought your use of haptics, especially the Caterpillar one, very good. I'm curious, a lot of people, I feel like now use these wireless charging banks, and instead of being like a cheap pad, it's like on the back of your phone case. You know what I'm talking about?
Yeah.
So do you think that this kind of attack is applicable there? I feel like that's where you could address the generalizability thing. Like you might always have that app on, even if you don't publicly, slap on like a charging.
Yeah, definitely. In that case, it would be a lot easier to kind of have that on people's systems.
Yeah.
But if you have like, I'm just thinking about it, if it's on someone's case, then you need some way of like transmitting that information to like a malicious entity. So it might be very bulky and having like a integrated microcontroller on it with the transmitter and the receiver.
It's
Might be really
probably
cool.
going to be a lot less covert.
I actually disagree with both of
Oh.
those things. On a battery, right, there's probably already going to be some sort of current sensing to make sure that you're not going to blow up your lithium battery. So it might be actually really easy to do.
You can probably just record it internally and then
Yeah.
sometime later you can send it but the problem is, so their idea is like you go to airport or
Yeah.
these public places and start charging and then the attacker can, penetrate those systems. But the case one, essentially the manufacturer has to be malicious, right?
Or maybe alternatively, like if you just leave your phone out in public, someone just swaps the case.
Yeah, something like that. Like the case itself by design has to be malicious. Right. Someone wants to kind of like wire you, like wiretap you, and try to kind of steal some information, that's possible. All right, guys, thank you so much. See you guys next week.
Years.